endocrine pathophysiology. So this will be a much wider perspective. We're going to cover the various parts of endocrinology and how disorders can happen, what are the normal physiology. So Dr. Alapan, what are the more common causes of endocrine disorder that we see?
We mostly see disorders like growth, short stature.
No, you're talking about the classic. I'm saying that from a pathophysiological perspective, what all problems can cause endocrine deficiency, let's say. Let's start with deficiency.
So deficiency could be due to the inadequate production from the gland, or due to that inadequate production could be due to the destruction of the gland or any antibody blocking or something that is not producing enough. Disorder could be due to antibody binding globulins that are taking the antibody to taking the hormone to its working place. Disorders could be due to the receptor at the receptor level, whether the receptor is not present, whether any antibody is there, whether resistance is there, or post receptor can be some issues like PHP, where post receptor.
So if you start off first, you didn't talk about the developmental issue. The gland is not developed properly. Second, the gland is destroyed, which you talked about, surgery, trauma, not just autoimmunity, there can be a lot of other causes which can cause that. Then gland is there, but the hormone is not being produced. Then hormone is there, it has not been transported. Hormone is reaching the target tissue, but it is destroyed because of the enzymes. Receptor is not there. Post-receptor problem can be there. What could be the problems of excess? Like when will you have excess in that perspective?
Excess hormones.
Yes.
If feedback inhibition is
So let's go start from the beginning, from the gland.
if more stimulation
Yes.
from the hypothalamus,
From anywhere. We are talking about generic conditions, so not hypothalamus.
if more secretion of hormones
Yes.
there, no regulation or of that hormone is present.
Okay.
Up regulation of hormones, receptors.
Receptors are more active, or receptor is acting without the ligand. The gland, so the gland is producing more, very simple, whatever reason. The gland is damaged and you have the store which has come out in the blood circulation. Your binding globulin is less, so you've got more free hormone. The hormone is being activated more at the peripheral site. Your receptor is hyperactive, or there is a post-receptor modification. These are the broad ways, and we're going to talk about the various aspects from that perspective. This is a very important session from that perspective, because this is going to talk about the entirety of pediatric endocrinology, and we will be focusing on different aspects from that regards. So that becomes important from that regard. So first of all, what really is a hormone? What do you call a hormone? So let's say pepsin is secreted by the gastric gland. Is that also a hormone? So what are the main three features of hormones? So one, it is produced at one part, acts on the other. That's a very, very important part. So it's a remote actor. Second, is it secreted into some particular secretion, or where is it secreted? It is secreted directly in the blood. So it's a ductless. That is the basic principle. When you say endocrine, it's like a ductless well. Exocrine goes to a system where it is secreted. And third, is it secreted in a huge amount? So it is in a very small amount. So conventionally, hormones were defined as substances which are produced in trace amounts in one part of the body, and they act on the distant part of the body through the blood. So this is the definition of hormones. Now, calcium is basically there. It is released from the bones, and it goes to the parathyroid gland to suppress PTH secretion. So it is produced in trace amount. It goes through blood, goes to a distant aspect. Is it a hormone?
No, it's not a hormone.
So then how does this definition, how do you define that then hormones? Leptin produced by the adipocyte goes to the hypothalamus and acts. That is an hormone. But why not calcium?
Because it's a trace element that is present.
So what? So when you're saying definition is a chemical which is produced in trace amount at one point, goes to the other in the blood and acts on the other, doesn't it justify that? So how would you like to change the definition? So calcium is a
Mineral, it is.
nutritive signals. So when you say glucose, calcium, fatty acid, these are all going to work like that. But then you're not going to call them a hormone because they are nutritive signals. So non-nutritive signal is a key word to remember in terms of hormones from that perspective. Now, how is hormonal regulation different from the other big regulatory process, which is the neural system?
The neural system follow from synaptic junctions
Yes.
to synapse. Hormones can act.
So neural is from a connected, so it's like a wired network. While hormones are like a Wi-Fi or a wireless network in the sense they can go to any part of the body and act from that perspective. So that's the major difference. First, second, which is faster?
Neurons.
Neurals will of course be much faster, and regulation also will be more tighter in terms of neural control, because only the neural secretion you can immediately switch on or switch off, while hormones they will be released in large amount and then they will go across the body and then act from that perspective. Now, Dr. Vibha, hormones are secreted. Let's say you've got growth hormone, the level in the blood is the same. Now, what decides it will have effect on one particular part and not effect on the other part? So, what makes hormone action specific?
The presence of specific receptor that
Most important is the receptor. What else?
presence of ligands specific to that
So,
hormone.
no, ligand is growth hormone. So, let's say growth hormone is there. Why is it only acting on the, let's say, chondrocyte, only on the liver? Not, let's say, I'm not saying it doesn't act, but let's say on the Leydig cell.
This hormone on the liver and the kidney, because in the liver they will secrete IGF-1 on the.
So you have said one very important, that there is receptor there. Second important thing is that the binding protein may guide them to particular sites. So that is there. What can prevent the action also? Let's say cortisol is going to act on the bone, on the muscle, on everything, but it is not going to act on the renal tubule where the epithelial sodium chloride channel is, where only aldosterone will act because of
The presence of somatostatin.
no, the cortisol.
Cortisol,
So cortisol is acting, but it is not acting in mineralocorticoid responsive tissue because of the 11 beta HSD. So you may have inactivating enzymes which are acting like a shield. So there are ways which make the hormone action specific, while neurons, if it is connected, is going to act from that regards. So as we discussed, hormones are non-nutritive chemical signals secreted in trace amounts at one point, which go and act on the other situation, and they go on the bloodstream. That is the endocrine, exocrine. That was the earlier definition from that perspective. Now, what is the total amount of hormones which is there in the whole body?
Like a full of tablespoon.
So it is somewhere around 5 grams. If you have each and every hormone which is circulating, if you talk about cortisol, it is in micrograms. If you talk about aldosterone, it is in nanograms. Some will be picograms. So it's like extremely low amount. So the hormone level in the whole body will be less than 5 grams entirely, and we can't imagine the life which is without that. Which is the most abundant hormone in the blood?
Thyroid.
Thyroid means what?
I don't know.
T3, T4, TSH, which one?
T4.
So T4 will have much more abundance from that perspective. Now, endocrine system basically regulate the whole amount of systems, but then we can classify them into two parts. One is the acute regulation and the other is the chronic regulation. So you've got the calcium, which is regulated. They're affecting the bone strength. They are regulating volume and salt. So calcium, glucose, volume, salt are acute regulations. While other things like growth, puberty, reproduction, those things will be more of chronic ones. So hormones are involved in multiple processes. We'll discuss about that. And they very importantly link the nutrition to metabolism. If you have got more energy, you will store it. If you've got less energy, you will use that store. So you've got various hormonal systems which will decide which way the body is going towards anabolism or catabolism. And of course, they are important. So when we talk about chemical messengers, we know that the chemicals basically will go and act at a distant site. This is known as the endocrine mode. We all know about that. There are other ways also in which they act locally also, which is known as the paracrine effect. And of course, there is an autocrine effect in which it is going to act about the same scenario. The same hormone can have an endocrine, paracrine, or autocrine effect. It's not that there will be different aspects which will be covering that. So when we talk about paracrine signaling, it is very important for local regulation and local control. So the signal will basically be bound to binding protein. Now, why is binding protein essential for paracrine signaling? And what are the classical paracrine mediators? You can name a few of them.
IGF-1.
IGF-1, you can say yes. Most of the growth factors. IGF-2 will be even better because IGF-1 actually is produced in the liver and then it goes to the bone. So it is actually acting mainly into the classical endocrine form. But paracrine, let's say IGF-2. So why do these paracrine signalers have a binding protein with them?
So that they reach to a particular site.
No, they are produced there only. So suppose you have got IGF-2 which is produced near the growth plate. The binding protein is important to ensure that they remain there. Otherwise, they will be secreted outside. So it's like trap. So they are going to trap that signal there, and that's why the scenario will happen. So binding protein will trap them there, take them to their receptor, and act from that regard. So they are like chaperone protein. Now these signals will not go out because of the overall homeostatic process, and that's important. So they have a localized process, tightly regulated, and that's why they have a selective action from that regards. Now when we say an endocrine ligand or a signal, this signal will have to go ultimately through the blood. Now we know broadly speaking that there are two types of hormones. We have got peptide hormones which are going to go through the blood easily. They are good swimmers, while we have got the ones which are the lipid derivatives. They will have a hydrophobic nature. So they will not be able to move through slowly. From there, these signals are going to act on specific scenario on the receptor, and they can have multiple actions as well where their action may be there. So endocrine signaling is made specific, as Dr. Vibha was talking about, whether you have receptor or not, whether they are activating enzymes or not, or inactivating enzymes are there or not in that perspective. So that's why compared to neurotransmitters, now you were saying that there is 5 grams of the overall hormones. How much neurotransmitters you can detect in the blood?
Very less amount, sir.
So norepinephrine, epinephrine, how much is there? You do in the blood test na, for metanephrines. They are extremely low. So they are even lower because they are very, very specific. They are released at that point. They are more like a very local action. While hormones, the growth hormone from the brain has to go entire the body. So that's why the amount is more. As you go down the tropic level of hormones, is the amount of hormones more or less? So let's say GHRH, GH, IGF-1, or let's say GnRH, LHFSH, estradiol. There is which will be the highest and which will be the lowest in terms of amount?
In terms of amount, gonadotropins will be higher if we talk about the gonadotropin axis, because they have to travel from pituitary to long.
And estrogen?
And estrogen will be much
They
higher.
will be
also
much higher. Na?
Because they have
So it is like food chain. You can say it is like GnRH has to be very small. It has just got to go from hypothalamus to anterior pituitary. That is it. From there, you have to have much wider picture from that regard. So that becomes important. The other thing, as I said, receptor based and local metabolism. These are the two factors which will decide, okay, this hormone is going to act here or not. Now, testosterone is a classical example. Testosterone is a pro-hormone. In a way, it can act also to the receptor, but it is either converted to DHT via 5-alpha reductase, or it is converted to estrogen using aromatase. So if some tissue, the 5-alpha reductase is more, you will have more androgenic action, while if aromatase is more, you will have more estrogenic action. And then of course the receptor of DHT receptor or the androgen receptor and estrogen receptor will also decide from that regards. Remember that hormones can have multiple effects. It's not that you have got single hormone will have single effect. So growth hormone, as discussed, classically acts on the growth hormone receptor in the liver, where, and we'll talk about the types of receptors in much more detail subsequently, where it will stimulate the whole process of the JAK-STAT pathway to produce IGF-1, and IGF-1 then acts on the growth plate to cause increased growth. So this IGF-1 is actually considered to be the main mediator of growth hormone. This is also known earlier as somatomedin, because it's going to work through the growth hormone, or sulfation factor because it was discovered on chondrocyte sulfation. But the growth hormone action is not just there. It has got multiple effects as well. Growth hormone also has an effect on growth plate through the growth hormone receptor, and the local production of IGF-1 here, what you're talking about is that here it is the paracrine effect. So IGF-1 here has a paracrine effect as well. And then IGF-1 produced will also act on the cell itself. So the same IGF-1 has got both endocrine, paracrine and autocrine effect. Now what it is telling you is that if you give IGF-1 via injection versus growth hormone, which one will work better? Why?
The multiple actions of present.
So you will also have local IGF-1 production which will be there, and there are IGF-1 independent actions also which are there on growth hormone. So that's why giving growth hormone will be better. Tell me one more reason which I have not talked here. Okay, with IGF-1 true. What else?
Chances of tumor.
Yes, why?
The IGF binding protein will not be there.
Yes, very good. So growth hormone is going to increase both IGF-1 and BP. So both of them will go up, while if you're giving only IGF-1, free IGF-1 will go up. So that is why children treated with IGF-1 are supposed to become coarser, their hair become thicker, and theoretical risk, I'm not saying the risk of malignancy is very high, it's not that, theoretically they will have a higher risk of malignancy. So wherever growth hormone and IGF-1 both are acting, you would prefer growth hormone. IGF-1 is only indicated where growth hormone is not going to act, genetically proven growth hormone resistance, or you have got the antibodies to growth hormone and GHD1A. That is the scenario. So these are the various types of hormones. Now, what also you need to remember is that, as I discussed, that one hormone can have multiple effects. Multiple hormones can have the same effect also. So if you remember allelic heterogeneity and locus heterogeneity, which we discussed in genetics, there is also some sort of a convergence of signaling pathway as well. The classical example is the type 1 PTH receptor. So PTH basically acts on the type 1 PTH receptor to largely regulate calcium metabolism, calcitriol production and phosphorus reabsorption, while the PTH related peptide is an antenatal paracrine factor, which is very, very important to mediate the chondrocyte growth. So if you have a problem of PTH, Alapan, what will happen to a child? Newborn. Born, fetus, first day, what will happen to this PTH deficient child? There's no PTH.
Hypocalcemia chances.
It will happen sometime. What will happen to his overall body shape, structure, bones?
Such
No problem will be there. But if the PTH receptor is gone,
then the skeletal chances of skeletal.
then there will be no bone growth. So this is known as Bloomstand's chondrodysplasia. So very important to remember is that PTH, GH, LH, a lot of these things have no role during your antenatal period. They start working when you are born. They want to maintain your glucose, your calcium, everything. While many of them like PTH, RP are very crucial in the fetal period. If it is deficient, no cartilage is formed. So it's a lethal form of chondrodysplasia which will happen in that regards. The other thing, of course, is pleiotrophy. You can say it is more like allelic heterogeneity. The same gene is regulating a number of processes. Thyroid regulates bone strength, brain function, heart, thermogenesis. So single disorder will have huge manifestations. So a lot of people talk about hormonal disorders as the widest range as far as the phenotypes are associated, because if you neuro, you know that there will be few things: weakness, muscle weakness, neuropathy, sensory, motor. If you have cardiac, you will have cardiac failure, arrhythmia. But hormones, you can have anything. So thyroid problem, you have all seen, can have from head to toe, anything can be there. And some people say this is one system where both sides of the diaphragm may be affected. So this is the classical scenario. The other very important thing is redundancy. What redundancy means is that for very crucial processes in the body doesn't want the problem to become catastrophic. So there are multiple hormonal systems regulating the same process. The classical example, of course, is glucose. So in glucose, we know for countering hyperglycemia, there is only insulin. To counter hypoglycemia, there are four hormones: growth hormone, cortisol, epinephrine, and glucagon. So if one is defective, the other will take over it. So if you want to know this process is more important for humans or not, all you need to look at is how many hormones are controlling it. So there are four hormones controlling. So glucose lowering is something which is more dangerous than glucose increase. So how many hormones are controlling salt loss?
AVP.
Yeah. Salt loss. Okay, you can say salt status, but yeah, what else?
ANP.
No, salt loss. So, which is countering hyponatremia? Let's say simple terms.
Renin.
Aldosterone is the major process. And then if you talk about volume, if you want to add there, you can say AVP will come into the picture. You will have angiotensin 2 coming into the picture because thirst mechanism is regulated by that. Now, how many hormones are regulating high volume and high sodium?
Atrial natriuretic.
Only one. And which is more potent, aldosterone or ANP?
ANP.
Aldo is more potent. So the body has evolved in conditions where sodium deficiency is common. That is why hyponatremic defenses are more strong. Calcium, if you compare hypocalcemia, you have got
Parathyroid.
and
Vitamin.
and hypercalcemia,
Oxytocin.
which is stronger? Okay, so in which condition calcitonin levels go very high? With one specific condition where calcitonin is used as a tumor marker. So what should happen in those patients if calcitonin is very high, it is very strong? Calcium should be?
No.
But do they have hypocalcemia? No. You remove the whole thyroid. What will happen to calcitonin? No, calcitonin is not there. So when you're removing thyroid, you don't have any calcitonin. But does the calcium go up? No. So it means that it is a very, very weak layer. So if you just look at it, if you are in the jungle, whether you are more likely to develop hypocalcemia or hypercalcemia, hyponatremia or hypernatremia, fluid depletion or fluid excess, hypoglycemia or hyperglycemia, you need to know that mostly low will be more common. Low calcium, low sodium, low fluid, low glucose. So all the evolution is towards preventing lows. For highs, we are not good enough. That's why we have got more diabetes now. We have got more hypertension now. We have got more fluid overload now. So this is the mechanism which is there. So if you talk about redundancy from that perspective, insulin is the only one which is regulating hyperglycemia, while epinephrine, glucagon, cortisol, and growth hormone, they are all acting against hypoglycemia. So this is